Hi everybody, this will be fun. I get to show you all about the angles in regular and irregular polygons. First we ought to talk about what does it mean for a polygon to be regular. A polygon is said to be regular if and only if it is equilateral and equiangular, if all the sides are the same as each other and all the angles are equal with one another in measure. We're going to talk about some regular ones and some irregular ones. I'm going to show a diagonal and rectangle ABCD and use the triangle sum theorem to find the sum of the interior angles. That's a pretty basic thing to do. Take a look here. If I show just a diagonal, you see it creates two triangles. And this triangle would have interior angles adding up to 180 degrees. And this triangle would give me another 180 degrees. So when I look for the sum of the interior angles, I really have 2 times 180 degrees, because I got those two triangles. And you probably knew this already, but the sum of the interior angles in any quadrilateral is 360 degrees. Probably worth remembering. And it asks me, since the rectangle is equiangular, all the angles are the same as each other, give the measures of each of these angles. And I think to myself, well, they add up to 360, and there are only 4 of them. So I would just do 360 divided by 4, and that'd make them 90 degrees each. And that makes sense, doesn't it, that it would each be right angles in the corners on that rectangle. Give the measure of each exterior angle and the sum of the exterior angles. Doesn't seem important now, but it's a good idea that we look at this early on. So I'll extend aside. And there I have an exterior angle. Nothing fancy, but you know that exterior angle would be 90 degrees, wouldn't it? It is the supplement of the interior angle. That'll always be true. And if that angle's 90, the measure of each exterior angle would be 90 degrees. Now what about the sum of the exterior angles? Well, they're 90 degrees a pop, and I got 4 of them. So that'd be 360 degrees, huh? So, you know, we were talking about regular and irregular polygons. Is this a regular polygon? It is equiangular, but it's not equilateral. So, no, this rectangle is not a regular polygon. In fact, the only regular polygon, the only regular quadrilateral would be a square. But here's a regular pentagon. Let's play with it for a minute. I think to myself right away, n is equal to 5. 5 sides, 5 vertices. How many diagonals can be drawn from a single vertex? And I'm thinking they can only draw, well, I can't go from P to itself. I can't go from P to Q. I can't go from P to T, remembering that a diagonal goes from a vertex to a non-adjacent vertex. Yeah, only diagonals I can show from vertex P would be to S and to R. So diagonals drawn from a single vertex, I can show 2. How many triangles are formed? I see clearly here I have 3 triangles formed. Give the sum of the interior angles. And the thought should be that we have 180 in this triangle, 180 in that one, and 180 in this triangle as well. And you could add those angles up just like you'd expect. The sum of those 2 angles gives me this. And so we have 3 times 180. And that gives me 540 degrees. For the sum of the interior angles in any pentagon, any pentagon will have the sum of the interior angles 540 degrees. Give the measures of each interior angle in that pentagon. And if they're all the same as each other and they add up to 540, I think I can handle that. 540, I just can figure out how big would each one be, so I'll divide by 5. And that would force each interior angle to be 540 divided by 5 is 108 degrees. So this angle right there would be 108 degrees. All of these full angles would have been 108 degrees. This one as well. Give the measure of each exterior angle. Let me extend that side so I can get a look at an exterior angle. There's an exterior angle on this polygon. It is always going to be the supplement of the interior angles. And the supplement of that 108 degree angle, the measure of each exterior angle, the supplement of 108 would be 72 degrees. But then give me it asks for the sum of the exterior angles. And I know that there are 72 degrees each. And I know that I have 5 of them. So I just got to do 72 times 5. And that's 360 degrees again. Hold that thought. There's some commonalities between these various polygons. Let's look at the regular octagon. And then we'll make some generalities here. How many diagonals? Well, let me think before I go any further. Octagon, I got n equal to 8. Because I'm really going to work off of the number of vertices, the number of sides. I'm going to work from that value of n. How many diagonals can I draw from a single vertex? Well, I went from vertex A. I think I can draw 5 of them. I'll just take a look at that real quick. 3, 4. Yeah, I can draw 5 of them. Had to leave those 3 out. The diagonals from a single vertex, I can get 5 of them. How many triangles does that create? And every time, well, I have 6 such triangles, don't I? How many triangles that creates? It creates 6. Always one more than the number of diagonals that I had. 1 diagonal gave me 2 triangles. 2 diagonals gave me 3. 5 diagonals gave me 6 triangles. And then it asked me for the sum of the interior angles. I got 6 triangles. And 6 times 180 degrees each gives me a total of, for the sum of all the interior angles, to be 1,080 degrees. So that's stuff I can remember about octagon, but the sum of the interior angles is always going to be 1,080 degrees. Give the measure of each interior angle. How big would this full angle be right there, or this full one right there? And well, it ought to be that 1,080 divided by 8. And I got a calculator for that, but I think it's going to give me 135. I just want you to witness that this is true. If I did 1,080 and I divided it by 8, I get 135 degrees, huh? So that's how big this interior angle would be, or this one, or that one right there would be 135 degrees. Then it asks for the measure of the exterior angle. Allow me to extend aside, get a visual on that. Oh, there's about an exterior angle there, missed it a little bit. But it would be the supplement of that 135, so the measure of each exterior angle would be 45 degrees. And it asks for the sum of the measures of the exterior angles. Well, they're all going to be 45 degrees, one at every vertex. So I got 45 degrees times how many vertices have you got? I got 8 vertices. And 8 times 45 is 360. And that's the beautiful thing about polygons. The exterior angles always sum to 360. We have not proven that, but I'm telling you it's true. Here's some generalities about polygons. Let's agree a polygon has n sides. We're going to build some formulas. So it would have how many angles or vertices if it's got n sides? It'd have n angles and n vertices. How many diagonals could you draw from a single vertex? Well, I'd have to, from this vertex, I got to leave 3 of them out. And from every time you want to draw those, so it's going to be n minus 3 diagonals from a single vertex. But how many triangles would that create? And I'm thinking back here, 1 diagonal gives me 2 triangles, 2 diagonals gives me 3, and 5 diagonals gave me 6 triangles. So it gives me 1 more triangle than I had diagonals. I got to add 1 to this, and that tells me n minus 2. N minus 2 triangles are formed. Give the formula for the sum of the interior angles. Well, I got n minus 2 triangles. And every triangle gives me 180 degrees. So that's the formula for the sum of the interior angles. That's worth writing down. Worth memorizing even. Sum of the interior angles is n minus 2 times 180. If the polygon were regular, and therefore predictable, I can make decisions about each of the angles, then each interior angle would be, and if I get that sum, n minus 2 times 180, and divide by how many angles I got, and I would have n angles, and that would be the formula for each interior angle. Worth making a note of that formula right there. And then we ought to find the time to use these formulas for a minute. Let's do that now. Got to think through these and do them with some care. The sum Give the sum of the interior angles at an 18 gon. Right off the bat, I'll be thinking n is equal to 18. And somebody wants the sum, I'm sure that's what he wanted there, the sum of the interior angles. That would be n minus 2 times 180. That's the formula to get the sum of the interior angles. So that would be 18 minus 2 times 180. That would be 16 times 180. I'll hit that with a calculator for a moment. Clear all the junk and go with 16 times 180. And we find 2880, 2,880 degrees for the sum of the interior angles in an 18 gon. Give the measure of each interior angle, and I'll have to take all the interior angles added up to 2880. I'll divide by how many I got, and I got 18 angles in an 18 gon, so I'll divide that by 18, and that'll give me the measure of each interior angle. I'm going to go hit that with my calculator again, the 2880 divided by 18. That gives me 160 degrees for the interior angles. Now, if you're thinking with me for a minute, if the interior angle on this polygon is 160, how big would that exterior angle have to be? Be the supplement, wouldn't it? That would have to be 20 degrees. Give the measure of each exterior angle, and if the interior angles are 160, then the exterior angles would have to be 20 degrees each. And the sum of the exterior angles? Well, gosh, I got 20 degrees on each one, and I got 18 of them. So 18 times 20. Interestingly, I still got 360 degrees, don't I? Yeah. The exterior angles will always sum to 360. It's a beautiful thing about polygons. Consider a regular 15 gon. Right off the bat, n equals 15, doesn't it? Give the measure of each exterior angle. This is a beautiful way to attack a polygon. First time we attacked it from the inside, here we're going to attack it from the outside. We're going to start with the exterior angles. I know the exterior angles add up to 360. And in the 15 gon, I'd have 15 exterior angles. So I just got to figure out how many 15s there are in 360. And I'm thinking that's 24. Because 30 would have gone into 360 12 times, and 15 is half of that. So, yeah, that'll be 24. The measure of each exterior angle will be 24 degrees. And the measure of each interior angle? Let me think about this. Here's my polygon. Here's over here my polygon. And the exterior angle is 24. How big would that interior angle have to be? He said, well, it's got to be the supplement of 24, and I guess that'd be 156, wouldn't it? Yeah, the supplement. So the measure of each interior angle in that polygon would be 156 degrees. Then it asks for the sum of the interior angles. I think we can approach this in two different ways. If they're all going to be 156 degrees, and how many you got in the 15 gon anyway, I guess you got 15 of them, then I'll be able to multiply 156 times 15. Let me do that real quick and give you a look at it. 156 times 15 would give us the sum of the interior angles. That's kind of hard for you to see, but I'm telling you it's 2340. But there was a formula for that, wasn't there? N minus 2 times 180. And since n was equal to 15, that'd be 15 minus 2, that'd be 13 times 180. So let me hit that with my calculator, see what that does for me. And gosh, I wish you could see it too. I'll do it here, maybe you can get a look at it. What if I did 13 times 180? Oh, still the same amount, isn't it? Still 2340. Still, that's the sum of the interior angles, is 2340. So you can attack these polygons from the interior or from the exterior. It is nice to know that the exterior angles always add up to 360. Let's work a few more together. The sum of the interior angles in some polygon add up to 1440. How many sides does this polygon got to have? And I would think, well, this is the time when I've got to use that formula, n minus 2 times 180. That's the formula for the sum of the interior angles. And if the sum of the interior angles was 1440, then this would have to equal 1440. And then you start looking at this, and should I multiply that 180 through the parentheses? And I say, no, there's no real reason for that at all. This is going to divide both sides by 180. We're going to find the value of n. Got to figure out how many sides this thing has. Now here comes an interesting thought to me. Must n be a whole number? Could like 7, 8, 9, 10, or 12? Or could it be 6.5? Could n be 6.5? And I say, no, it cannot be. If n represents the number of sides, you cannot have a fractional number of sides. You can have 6 sides or you can have 7 sides, but you can't have 6.5. So this has to divide evenly, and I'm pretty sure that it will. We'll take a look at that. But we got 1440. Divide that by 180. And 1440 divided by 180 gives me 8. So n minus 2 is equal to 8. I'll add 2 to both sides, and I got n is equal to 10. Yeah. So it must have been a decagon, huh? How many diagonals can you be drawn in that polygon? Oh, well, that's a different question, isn't it? I have to go back to the other formulas that we learned in the other video. Diagonals from a single vertex was n minus 3 times how many vertices you got, n. Don't count anything twice. So I would use this formula to figure out how many diagonals could be drawn in that polygon. I know the polygon's got 10 sides, so that'll be 10 minus 3 times 10 divided by 2. And that's really just going to be 7 times 10, there's 30. 7 times 10, there's 70 divided by 2. There's going to be 35. So 35 diagonals could be drawn in that polygon. That has the sum of the interior angles, 1440. Let's play some more. Each interior angle of a regular polygon has measured 168 degrees. How many sides does that polygon got to have? I'm going to do this a couple of ways. You might think of the quickest way first, but let me just think. Isn't there a formula for the sum of each interior angle? And there is. It's n minus 2 times 180 divided by n. That should equal the measure of each interior angle. But if each interior angle is 168, let's set those equal to each other, see what comes. And the first thing I would do is multiply both sides by n, which would leave you with n minus 2 times 180 is equal to 168n. Here you got to multiply through the parentheses, and that gives me 180n minus 360 equals 168n. Let's clean this up. I think I'll subtract 168n from both sides, and that would just leave me 12n here minus 360 equals 0. Bring that 360 to the other side. I got 12n is equal to positive 360. Divide both sides by 12, and I'm convinced that n would be 30. This thing had to have 30 sides, I guess. Yeah, there was a quicker way to do that, wasn't there? You were probably thinking it all along. If we thought that the interior angles were each 168, that's what we're given here. And we worked that with this interesting formula, and we were able to figure out how many sides it had. 30 sides. But if you would have thought, if the interior angles are 168, how big are those exterior angles going to have to be? Yeah, the supplement of 168 got to be 12 degrees, huh? And since the exterior angles always add up to 360, we could take that and divide by the measure of each of those exterior angles and see how many we would have. Yeah, 360 divided by 12 leaves 30. So n was equal to 30. That's a 30-sided polygon. Huh? That's fun. Let's do some more. We've been talking about regular polygons, but we have not talked about an irregular polygon much. Consider an octagon, a irregular octagon, and then we know it's got 8 angles, but it talks about 6 of the angles. And those 6 angles add up to 900 degrees. The other angles are congruent. Give the measures of those congruent angles. You think, in an octagon, I ought to have 8 angles. They're telling me about 6 of them. What would all 8 angles add up to? That's what I got to think about first. And I'll go with that formula, n minus 2 times 180. And that would be, in this case, since it's an octagon, I should write it already. N is equal to 8, isn't it? So 8 minus 2, there's 6 times 180. So the sum of the interior angles is 1,080 degrees. That's for all 8 angles. But 6 of them add up to 900. Let me take that 900 out of this 1,080. And you see I have 180 degrees left for the other angles to share. How many other angles are there? Well, we knew about 6 out of this 8 angle figure. So there must be 2 other angles to know about. And those other angles are congruent, and they add up to 180. So give the measures of those congruent angles, they'd be 90 degrees a pop, huh? They would have been right angles. Let's do that one more time. Here we have an irregular decagon. So right off the bat, we should be thinking that n is equal to 10. And 7 of the angles add up to 1200 degrees. The other angles, I figure there's 3 of them, huh? The other angles are congruent. What's their measure? Well, what do all the angles of a decagon add up to? I'm going back to n minus 2 times 180, because that gives me the sum of the interior angles. And 10 minus 2 would be 8 times 180. And that gives me 1,440 for the sum of the interior angles in a decagon. So, if that's 10 of the angles, let me subtract these 7 angles away. 1440 minus those 1200 degrees for the first 7 angles, and I'm left with 240 degrees for the other angles to share. Those other angles are congruent. How many other angles are there? Well, there were 10 in this figure, and we knew about 7 of them adding up to this amount. So there must have been 3 of them that are outstanding, and they add up